Yo, what's up, guys? Um, welcome, welcome to this new stream on my channel. Mr. XC2, what's up, bro? Glad to see you. Yo, let's go. Okay, yeah, so today we are continuing the 2D game series. And what we are doing is just that's just my engine, ignore that. Yeah, what we are doing is graphics with OpenGL, as you can see in the title, which consists of implementing like some kind of layout for a vertex buffer, index buffer, and vertex array, and shaders. Yo, Mr. McC, the real one, what's up? Glad to see you. Okay. Yeah, so if anyone is interested, I expanded like the engine a bit with you have things. Okay, like we had that sprite atlas texture, but now there are physics in the engine, which is really cool. So we have like physics, a physics engine, and the physics engine is box 2D. And yeah, I don't have a separate physics engine which I developed or something, cause like I tried to do that, but in the end it's like really doesn't make any sense, because like if there's something that blocks 2D, why you need a physics engine? I mean, yeah, so let's just add a sprite renderer, zoom in. Okay, so you can now add a rigid body, do a dynamic, and a box collider, so that it's really for us. Wanna see a meme? Yeah, sure. Okay, so we add an oh, didn't know. I don't know. Probably an assertion. Yeah, whatever. Okay. Yeah. Okay. Let me show this. Yeah. So where is it? Oh, it's not here. Wait, I see it in a sec. Just wanna show this. Okay, so no, not a sprite atlas. A rendered body. Do it dynamic. And a sprite renderer. Yeah, that's the wrong one. Okay, that's like this, and it's rotated like that, and do this. Oh, we don't have a camera, so let's add a camera. Ah, okay, we don't have a box collider here. We don't even have anything. So rigid body and a box collider. Nice. Yeah, so as you can see, 2D physics are working. Nice. Okay. Yeah, so yeah, let's keep on going with 2D game and YouTube. Okay, let me open the okay, let's first see the meme. Just block it. Me listening to the crab giving me a okay, that's satisfying. I like that. Nice. Okay. Nice. Okay, so in YouTube, let's just hit F5. Oh, we don't have that implemented. Yeah, let me just quickly open the dev folder. Cause like I made it for exactly that reason. Dev. So this is like the end product we're going to have today. Shaders and rendering something on the screen with OpenGL. That's very nice. Oh, okay, you need to eat dinner? Okay, it's okay. yeah, see you, Mr. McC. Yeah. Okay. So the first thing, let's make a new file in VS Code, which we're going to call launch JSON. Okay, we have like this JSON thing, and then we have a version, and then configurations, the launch configurations. We have those. That should work like this. And then we have name Windows launch. And we need a colon here. Nice. And we have the debugger type, which is CPP Visual Studio Debug, I guess it is. Okay, then we have request is launch, program which we want to launch. Yeah, that's that. Args is nothing. Stop at entry is false. Oh, we don't have a comma here. Current working directory is workspace folder / bin. It's not even the right thing. /bin /2d game. And this is workspace folder. Okay, environment is nothing. Like this. And console is an external terminal. Yes, okay, we need a comma here. Okay, we need a comma here as well. Okay, so that's our launch. So that's now we can press F5, and we have our window, which is very nice. Okay, so let me familiarize myself with this code. Okay, I hope you can see everything. I hope you can see the code. Yeah, let me see on my phone. Yeah, let me see on my phone. Yeah, it's pretty. Yeah, let me see on my phone. Yeah, pretty bad. Okay, let's increase the font size. Mr. I am not sus dog. What's up, bro? Glad to see you. What are you doing? I am yeah, I'm working on a 2D game for a tutorial series on YouTube. And today we are doing like graphics with OpenGL, as you can see in the title. Yeah, okay, so the first thing, let's make a graphics folder where everything is related to graphics. So we have graphics buffers. Oh. Buffers. .hpp. And we do hash pragma once. Then we do namespace game. Yeah. Okay, so yeah, now like let's say class vertex buffer, and like in OpenGL every like OpenGL object kind of has the same structure. So let's do that. Let's make a like some header for like graphics related stuff. So let's name it graphics core HPP pragma 1 namespace game, and we do using a render ID like this is equal to unsigned int, because like OpenGL render ID is an unsigned int. And then we do a interface class, like not an interface class but a class from which every OpenGL object inherits, which is named GL object, as a virtual destructor, which is public. Yeah. Then we have a inline. So in protected first, let's do a render ID ID or render ID, and then we have an inline render ID get render ID const return render ID. Easy stuff. Now we need a few virtual like pure virtual functions, which is virtual void delete object, which deletes the object from OpenGL. Yeah, let's do it equals 0. Virtual void bind equals 0. Like that, those are const functions. Virtual void unbind const equals 0. Okay, that's it for this header. Yeah, for the graphics core for now. Okay, so our vertex buffer inherits from GL object, obviously. So let's include never gonna get up. You mean get up from bed, or what do you mean? Yeah. Okay. So obviously, yeah, let's include graphics core, and the vertex buffer inherits from GL object. Nice. Okay, so first public vertex buffer constructor. Let's first make a default constructor and then vertex buffer. We have a few things we need to give in there, which is float vertices, because obviously vertices are just float pointers. Then we have a size, which is like the size of the vertices. And yeah, then we have a GL draw mode, which we're going to default to 0x88E4, which you may think, what the fuck is 0x88E4? Okay, we need to include core/defense. Okay, so 0x88E4 just stands for GL static draw. So we want to handle the buffer data as if it was static, and we want to handle it that way that the buffer data is not changing during runtime. So we don't change the geometry in the buffer. And the opposite of that would be GL dynamic draw. Okay, so we can do hash include glad and just do GL static draw, but I don't necessarily want to include glad here, because we just need it for this one define. So if you search GL static draw, you can see it's there, and you can just copy this right here, and then you don't need to include glad. Yeah. Okay, now we need a few functions. Yeah, first we need to override those. Delete object, const override, virtual void bind, const override. And oh, by the way, is the music? Is it too loud? Oh fuck, I think it is. I don't know. Let me see. Yeah, okay, I think it's okay. Sorry for that. Ah, yeah, it's okay because I have turned out the desktop volume. Okay, easy. Yeah, nice. Okay, so we have bind, then we have virtual void unbind, const override, like this. Void set data, which sets which resets the vertex data of the vertex buffer. So this is like the data we want to set, and then the size of the data, and then the offset to which we want to set the data to. So we have like this is our vertex buffer, which has like a lot of things in here, like this. And this is all of the data. And if we reset like the data at offset 0, we don't reset it exactly, but we set new data to an offset. So if we set new data to here, we would just append that data. But if we set new data to here, we would append it here. Or like if we do offset like 1, then we would append it here. So this is like the offset. Nice, okay. Yeah. Okay, so now we need to do like kind of have an API for we need to have an API. Let me see. Yeah, okay, that's good. Yeah, I don't want that. Yeah, okay, so we need an API for vertex buffer layouts, because every vertex buffer has layouts. Like, for example, in OpenGL, let me open Paint. We have like our big vertex buffer, which has like stuff in here. And obviously it's just a huge mess of data. Just a huge mess of 0, 1, 2, 7, I don't know, some weird coordinates. And we need to somehow say to the graphics card that we want certain parts to be certain things. So for example, we can do the first 3 floats of every vertex is the position of the object. Then the next 2, for example, is the texture coordinates. And the next 3 is like the normals. And this is like this is like the process of laying out the data of the vertex buffer, not just having a huge mess of data. So this is how you do it with vertex layouts. And obviously we also need to have a stride, because like it's still a huge mess of data, and we need to somehow say to the graphic cards where a new vertex begins, because obviously we send more than one vertex to draw. Like here's this one vertex, here's another one, and here's another one, and then we want to draw this triangle, and we send this vertex which has information, this vertex and this vertex, and this is all in one array. So in one, like not 2-dimensional, 1-dimensional array. And somehow we need to say where a new vertex starts, and yeah, then here the new one starts. So we need to say that to the cards as well. Yeah, so how do we do that? We can do that in like infinite amount of ways. Like you can do anything. It's very easy, but I want to do a nice and user-friendly API for that. So let's do that. So enum class, we have here enum vertex layout data type. So the data type of the vertex layout. We have int, we have a float, we have a double, we have a vector 2f, vector 3f. So this is like should we call it vertex layout or vertex attribute? I think vertex attribute is better. Okay, so for one vertex attribute, like how OpenGL should treat treat the data we give it to, because like if we send a if we say vec3, then it takes like this three things and like stores it in its own attribute, and if we say int, this is one int, it stores this int in its own attribute, and vec 4, for example, it stores those 4 values in its own attribute as well, in this layout of one vertex. So this is how vertex layouts work. There's one layout with multiple attributes. Okay, so and then we have vector 4f, and we have matrix 2x2 f. Let's just say it like this: matrix 3x3, matrix 4x4. Yeah. Okay, that's all we have for a vertex data type. Okay, we could do this because it looks better and makes sense to group it like that. Yeah, okay. This stupid thing doesn't let me to do that. Okay, so now we need a struct like for the real for like one attribute of the vertex layout. So we want to set attributes of the layout to make a layout, obviously, because layouts consist of attributes. So let's call it vertex layout attribute. That's a struct. Okay, we need a constructor. No, vertex layout attribute constructor. It has a name, which is like kind of just for debug purpose. Yeah. Then we have U32 offset, which is like the offset of the thing in the layout. Yeah, we could kind of automate that, I guess. Yeah, we could automate that. Let me think of a way. Okay, we don't need the offset here, I guess. Because... yeah, okay, I know how to like automate that. Nice. Okay, we need a name and we need a data type of the attribute. So is it a vector 3, for example, type, and that's kind of it. And then we need if it's normalized, which is like never the case, but it's like not never, but it's really rare. But let's do that as a default argument of false. So yeah, now we need a few of those member variables. So we have name is equal to nothing. Then we have U32 element count. So the element count of the so of the attributes, like for example for a vec3 it would be 3 elements in the attribute, for a matrix for x4 16, and so on. And stride, which is like the stride of one vertex. Yeah. Okay. So stride is just the size in bytes, how much it takes to like have one vertex in this array. So let's say one vertex consists of just like 5 values, one vec3 and one vec2, and then we have like a lot of them. Like if we have three vertices, let me see, we have this, and we obviously want to group them. We want to say this is one, this is one, and this is one, and we need a stride how many bytes it takes to get to the new vertex. So this is just a stride. Okay, so a vertex layout data type, and bool normalized. Okay, that's it. So let's initialize them. So name is name, type is type, and normalized is normalized. Easy. Okay. Forgot a comma. Yeah, okay. Nice. Let's do data size is equal to 0, because we need that. Like the size of the data is how much one one element has, like what is the size of one element in the attribute. Yeah, the size in bytes. For example, it's like almost always it's just floats, but like for a double it would be 8 bytes. So yeah, the data size. Okay, so yeah, we could do that. Data size is equal to 4 because it's equal to size of float. And if yeah, let's do that. Type equals vertex data type double, size of double is size of float. Yeah, nice. Okay, so we switch on the data type now, because we need one more thing, which is the element count, which we have here. We need to calculate that. So we switch on the type, and yeah, format. Thank you. And we do case vertex data attribute data type int, and case vertex attribute data type float, and case vertex attribute data type double. So if it's one of those, we do element count equal to 1, obviously, and then we do case vertex data type vector 2f. We do element count equal to 2, break, and we have case vertex attribute data type vector 3. We have element count equal to 3, break, case vertex attribute data type vector 4, or case vertex attribute data type matrix 2x2. Yeah, I'll be right back. Someone's calling me. Yeah, okay. Oh, nice. Okay, nice. So for a vector 4 and a matrix 2x2, 2x2 are like 4 elements, and for a vector 4 is obviously 2x2 is 4, and 4 is also 4, so let's do element counts equal to 4, and k is vertex attribute, vertex data attribute data type matrix 3x3, element count is equal to 9, break, and k is vertex attribute data type matrix 4x4, element count equal to 16, break. Nice, okay, easy. Yeah, that's it. So now we do stride is equal to data size times element count, because it's the size in bytes which it takes for one vertex, and element count is yeah, it's like the stride for this attribute. So this is the stride. Nice, okay. Easy. Yeah. Okay, nice. Okay, so now let's keep on going with our vertex buffer. Now privately we need, wait, let me see. Yeah. Okay, privately we need a std vector. Okay, we need a vector here. So std vector of vertex layout attributes, layout attributes, because a vertex buffer needs a layout with attributes. Nice, okay. And void set layout, we need an initializer list for that, because we want a initializer list. That's the way I did it. Yeah, we could do a vector, obviously. Yeah, but let's do it with an initializer list. So std initializer list. Yeah, okay, we don't need that. It's useless. Let's just do it with a vector. Vertex layout attribute attributes. Then we have an inline const std vector of vertex layout attribute get layout attributes const return layout attributes. Nice, easy. Okay, so that's it for the vertex buffer. Now let's do the index buffer. Class index buffer. An index buffer is just for indexing a vertex buffer, and yeah, like I'm not going to explain OpenGL stuff in this tutorial, because like I expect you have like OpenGL knowledge, because like making a game needs a little bit OpenGL knowledge. So we have indices, which is the data for the buffer, and then we have the count, how many indices there are in the buffer, and we have GL draw mode is again this guy. Nice. And index buffer like that. Okay, we do virtual void delete object. Yeah, we can copy that. And then we have one private variable, which is u32m count is equal to 0, and then we do inline u32 get count const return m count. Okay, that's it for the header. Nice. Okay, now let's implement those methods. Yeah, so those. Okay, hash includes graphics, buffers, namespace game, and we have yeah, the definitions of those functions. And let's remove that stuff. Okay, we need this. Oh, this equal default, we don't need that. Just copy that. Nice. Like that. Okay, nice. Yeah. So in the vertex of a constructor, what we do is first we need to include let. Yeah, okay, so let's also implement those methods. So remove that, remove that, remove that, remove that. And yeah, now we need index buffer column. Bind and unbind. And define those here. And by the way, we are not going to do shaders today, because I don't have a lot of time left. And we need a default constructor here. Nice. Yeah, okay, nice. So in the vertex buffer constructor, we do GA create buffers. We need to create one buffer, and render ID is the buffer we want to create. And then we do GA bind buffer, GA array buffer, which stands for vertex buffer, so we want to bind the vertex buffer and render ID. And then GA buffer sub data, no, GA buffer data, I'm sorry. GA array buffer is the sub data to which buffer we want to give data, not sub data. Size is the size of the data, vertices is the data, and usage is GA draw mode. Delete object is just GA delete buffers 1 and render ID. Bind is GA bind buffer, GA array buffer render ID. Unbind is GA bind buffer, GA array buffer 0. So this unbinds the currently bound buffer. GL bind buffer, GL array buffer, render ID, and then set the data, because we need to bind the buffer to set the data. So GL array buffer, offset is the offset, size is the size, and data is the vertices. Vertices. Why? Nice. Okay. So sub data, because we don't want to reset the whole buffer, we just want to set sub data. Yeah. Okay, set layout. This is just easy. Vertex layout attributes equal to attributes. Yeah. Okay, now the index buffer. Easy. We do count is equal to count. We initialize that, and then we do GA create buffers 1 and render ID. And GA bind buffer. Now it's a GA element array buffer, because like this is how OpenGL calls index buffers. I don't know why, but it is that way. So GA buffer data, GA element array buffer. Count times size of u32, because like the count is not the size, and we need a size in bytes, so we do the element count times the size in bytes is the actual size of the array, obviously, indices. And why do I have in the dev code select draw here? That's dumb. Draw mode. Nice. Okay, so index buffer destructor is just here delete buffers 1 and render ID. Where's... I don't have a vertex buffer destructor. Vertex. Why? Vertex buffer. here. Nice. GL deletes buffers 1 and render ID. Delete object does this. Bind does this. And unbind does the same thing, just with 0. Okay, that's it for the graphics buffers. Now we need the vertex array class. So vertex array.hpp, pragma1's hash includes core/defines and hash includes graphics core. And then we do namespace, no, not Kaima, namespace game. And we have a class vertex array which inherits from public GL object. Yeah, okay. Then we have a vertex constructor which doesn't take any arguments, and a destructor, and then we have that garbage right there. Yeah. Okay, so for private we have a std, so okay, we need to include vector and we need to include memory. So we have an std vector of std shared pointers, because we want to have vertex buffer and index buffer as shared pointers of, yeah, okay, we need to also include graphics buffers of vertex buffers like this. Vertex buffers. So the vertex buffers associated with that vertex array. std shared pointer of index buffer, index buffer, which is the index buffer associated to the vertex array, to this vertex array. Okay, now we need getters for those, so inline const std vector std shared pointer vertex buffer get vertex buffers const return vertex buffers. Then we have inline const std shared pointer index buffer return get index buffer const return index buffer. And then we have void add vertex buffer, which adds a vertex buffer to this which associates a given vertex buffer to this vertex array buffer. And we have no, let's not copy that. Void set index buffer const std shared pointer of index buffer. Nice. Okay. So we need to now make this vertex array.cpp. Do that. Implement all of those methods and do hash include vertex array namespace game vertex array we could obviously have like namespace graphics, namespace core or something, but I don't think it's necessary. Yeah. So let's do that. Let's implement all of those. Yeah, okay, we could do this guy. Okay, we replace all of these guys with this. Nice. Okay. Yeah, vertex array constructor just creates a vertex array with glad, like with OpenGL. Let me thank you. Include glad. This is GL create a vertex arrays 1 and render ID. GL bind vertex array render ID. This is all of the stuff we need to do. And GL delete vertex arrays 1 and render ID. Add destruction and delete it here. GL bind vertex array render ID. And we do GL bind vertex layer 0. Okay, so add vertex buffer. We do m vertex buffers dot pushback buffer. Then we do buffer bind. Yeah, first we do this bind. Why? Huh? What the fuck? I don't know. Yeah, okay, so we bind the vertex layer and the vertex buffer. And then, okay, I have what do I do here in this garbage? Okay, I use it here. And where's it ends? I get it. Okay, so I have found a bug in my dev code, but I'll worry about that later. So we do a for loop which goes through every get layer attributes through every attribute of the buffer. Yeah. Okay, so vertex layout attributes attribute is equal to buffer get layout attributes at I, and we have GL data type is equal to, let's do is equal to GL float, and if vertex data type we kind of already have the data type here. Type. No, we don't have it. Oh yeah. Okay, so it's float, and if vertex layout attribute vertex layer if attribute dot type equals vertex layout data type thingy double GL data type is equal to GL double, and else if attribute dot type equal vertex thing int, we do GL data type is equal to GL int. Nice. Okay, and then what we do is we need the offset as well. Okay, we have 32 vertex offset is equal to 0, and then we do vertex offset. Wait, let me see. Okay, we do vertex offset is equal to 0 here. Okay, we don't even need that as a member thing. Do U32 vertex offset in here. Yeah, and the stride. Okay, we need to get the stride as vertex stride, and we get that by just doing for auto attribute in buffer get a layout attribute. We do vertex stride plus equals attribute dot stride. Yeah, nice. Okay, and we do vertex offset plus equals attribute dot element count. But before we do that, we do GL vertex attrib pointer. The index is I. Attribute dot element count is how many elements are in the attribute. GL data type is the data type. Normalized is attribute dot normalized. The stride is vertex stride. Offset is yeah, we need to do void pointer int pointer t, because like we need to cast that to a void pointer, and this is vertex offset. Yeah, nice. Okay, and then we do gl enable vertex attrib array at I. Okay, yeah, hope that works. And set index buffer is just buffer. Yeah, this bind and buffer bind. And index buffer is equal to buffer. Okay, that's it for the vertex array. This is like the huge mess, which is a little bit hard. Okay, so let's do graphics